Today we have Dr. Sourav Maiti. He'll be presenting his work on carrier multiplication in low bandgap mixed tin lead halide perovskites. All right, Sourav, go ahead.
Good afternoon, everyone, and thanks for the introduction. So today I'm going to talk about my work on carrier multiplication in low bandgap mixed tin lead halide perovskites. I am a postdoc under the supervision of Professor Lawrence Sibeles, and my project is a consortium between TU Delft, Amol, University of Wageningen, funded by NWO, Toyota Motors, Surfix, and ECN. So the work is related to solar cells, and in solar cells we use semiconductor materials with a valence band and conduction band. Upon photoexcitation, we create electrons and holes, and then these are collected at the electrodes for photocurrent generation. So as a base material in solar cell, we use this kind of semiconductors where we can create the electron hole pair, and then they are collected at the electrodes. Now, most common material for photovoltaic applications is silicon, which has a band gap around 1100 nanometer. So it absorbs around 1100 nanometer and has a broad absorption spectrum. Now, although silicon has a broad absorption spectrum, there are some problems with silicon, and that I'll discuss in this slide. So in case of silicon, the band gap is about 1100 nanometers, and here is presented the solar spectrum in terms of spectral intensity versus wavelength, and we can see that the photons that are around the band gap are absorbed in silicon, but the photons that are below the band gap are not absorbed, which is about 20% of this total solar radiation. And the photons that are above the band gap are absorbed in the silicon, and they create hot carriers. So they have energy excess than their band gap. And this excess energy is lost as heat because these carriers thermalize very quickly to the band gap. So that is about 33% loss due to thermalization. And because of these losses, we have a Shockley-Queisser limit of about 30% in case of the silicon solar cells. Now, our idea is how to utilize this thermalized loss of 33% for photocurrent generation. So there are basically, it can be done in two ways. One is hot carrier solar cell, where the carriers can be extracted when they are still hot. And the other way is through carrier multiplication, where this excess energy can be utilized to create additional electron hole pairs in the band gap. So out of one absorbed photon, we can generate multiple carriers. So carrier multiplication is known in inorganic materials and also in organic chromophores in terms of singlet fission. And today I'm going to mostly talk about the carrier multiplication in inorganic materials. So here we can see that upon absorption of a high energy photon, we create a hot electron in this schematic, and then the electron can cool down to the band edge through phonon emission. And also this excess energy can be utilized to create another electron hole pair. So this excess energy is taken by another electron in the conduction band, and it generates an additional electron hole pair. So the carrier multiplication competes with the carrier cooling, and it has to be very effective in competition so that we can generate the additional carriers. Now, in terms of photovoltaics, on the left is shown the ideal behavior of carrier multiplication. So y-axis is basically quantum heat, that is the number of charge carriers created per absorbed photon plotted against the band gap multiple. That is the most common way of plotting carrier multiplication. So as you can see that when the below 1, the band gap multiple 1, there is no quantum yield is 0, then it starts to absorb and the quantum yield is 1. And then when we have energy twice the band gap multiple, it ideally goes to 2, stays there, and then it ideally goes to 3. So this is like an ideal staircase behavior. And on the right, it is plotted how it can benefit carrier multiplication can benefit the photovoltaic efficiency. So the black line is the Shockley-Queisser limit. And we can see if we have ideal carrier multiplications, the efficiency can go above 40% when the band gap is below like 1.3, 1.2 eV. So these are ideal case scenarios. But if we look at carrier multiplication in terms of like a realistic band structure, so this is like a parabolic bands with electron equivalent hole mass in a bulk material. Now, during carrier multiplication, the energy and the momentum needs to be conserved simultaneously. And for this reason, when we excite a electron from the conduction band, from the valence band to the conduction band, we create this electron and hole, and the energy is almost equally distributed between the electron and hole. So the threshold increases, and then due to the momentum conservation, the threshold becomes 4 times the band gap in this case. So if the threshold is 4 times the band gap, we lose a lot of, like we don't have much energies from the sun in that region, and it is not really useful for solar cell applications. So for example, in bulk silicon, the carrier multiplication threshold is about 6 to 7 times the band gap, and it's not really useful for solar cell. So we need to look for materials that are like good for carrier multiplication applications. So the property for carrier multiplication is like it has to have a suitable band gap between 0.5 to 1.3 eV to get like efficiency enhancement in solar cells. The threshold should be close to twice the band gap, and the efficiency should be near unity. So the carrier multiplication can compete effectively with the carrier cooling. And also the material has to have a high charge carrier mobility. It has to have long carrier lifetime, and the charge carrier needs to be extracted effectively at the electrodes. And this brings us to the perovskites. So perovskites materials have gained a lot of attention in recent times. It has a formula of ABX3, where A is a monovalent cation, B is a bivalent cation, and X is the halide. And this is a structure of the perovskite where the bivalent cation resides in the octahedra formed by the halides, and then the A, that is the monovalent big cation, resides in this cubo-octahedra. Now, perovskites are very like important in solar cell application because they have low exciton binding energy, so it's very easy to generate free charge carriers in this system. They have strong absorption coefficient, so they absorb a lot of light. It's good for making thin solar cells. They have long diffusion length and long carrier lifetime. It can be synthesized quite easily. So synthesis is low cost and it is facile solution processing. So most of the perovskite are based on methyl ammonium or formaldinium for A and lead for the B cations. Now in this methyl ammonium and formaldinium lead halide perovskite carrier multiplication is reported in literature. So this is for formaldinium lead iodide nanocrystal, and you can see the carrier multiplication threshold is quite close to twice the band gap. The efficiency is better than lead sulfide or lead selenide nanocrystals. And here it is from also reported in case of cesium lead iodide nanocrystals, also like perovskites, and the threshold is close to twice the band gap and the efficiency is quite good. But the absolute band gap of these materials are like 1.6 to 1.8 eV, and they are not really very useful for solar cell applications. So the band gap can be brought below 1.5 eV in tin lead halide perovskite. So some of the lead is replaced by tin, and then it still have very low exciton binding energy, so it generates free carriers very easily. They are stable, then they're pure tin halide perovskite, but there are issues with stability because they are not very stable compared to the lead-based perovskites. But the advantage is in terms of the band gap. To study the carrier multiplication, so we thought we can study carrier multiplication in these halide perovskites because the band gaps are very suitable, and we used simple spin coating method to synthesize the material. So all the components are mixed with a surfactant of guanidinium thiocyanate, and they are spin coated on substrate. Then they are annealed at 100 degrees to form this structure with a tin and lead ratio of 60% to 40%. That gives the band gap of about 1.3 eV. You can see the SEM image of this perovskite, like their bulk domains, and without any pinholes or loopholes in the structure. Now, to know more about the carrier multiplication, we use stranger absorption spectroscopy. So in this method, we excite the sample with a pump beam to create charge carriers in the sample. And then we look at the population of the charge carriers through a probe beam. Now, by delaying the probe with respect to the pump, we can understand how the charge carriers behave over time. So in the simple scheme, there are like 4 photons on the samples, and the sample absorbs 2 photons. So we create 2 excitons in the sample. Now, if we excite the sample with a pump beam, the pump already creates 1 exciton in the sample. So when the probe comes, the absorption of the sample decreases. And that we can see here also. The pump creates addition, like the already charged carrier. So when the probe comes in around the band gap, it sees a depleted ground state, and this results in a bleach or negative change in the absorption. So here it is shown, like where the sample absorbs strongly, we see a bleach around the band gap. And then when the pump fluence or pump intensity is low, this absolute intensity of the bleach divided by the number of absorbed photons is actually equal to the quantum yield. So it is equal to quantum yield and the absorption, the bleach cross section. So if we monitor the delta A divided by I0FA, then we can have an idea about the quantum yield in the system. So this is the absorption spectrum of the perovskite that we synthesized. The band gap is about 1.28 eV. And these are the arrows represent different pump excitation energies. So we excite below twice the band gap, and there should not be any carrier multiplication when we excite below twice the band gap. So these are our reference points. And then as we go above twice the band gap, we should start to see the carrier multiplication if there is any carrier multiplication. So here in the plot, I have shown that delta A divided by I0FA as a versus probe energy for our system, and we see for 1.38 eV excitation that is close to the band gap. So the spectra, we see the ground state bleach, and the spectra doesn't change much over time because we create carriers in the around the band gap. Now, when you excite at high energy like 3.54 eV, which is more than twice the band gap, initially we see a huge photoinduced absorption in this region. That is because of the band gap renormalization effects. So when we create the carriers, the band gap becomes smaller in this material, and we start to see additional transitions at early times because of the hot carriers. Now, as the carriers cool down, about 15 to 20 picosecond, we see the shape of the bleach is quite similar to the shape of the bleach around 1.38 eV excitation. And we can see the intensity of the bleach is higher compared to 1.38 eV excitation. So this gives us an indication that there is carrier multiplication in the system, because delta A divided by I0FA directly gives the quantum yield. So we plotted delta A versus I0FA for different photon excitation energies, and we see as we go above twice the band gap, the slopes start to increase. That means we are getting more and more carriers out of one absorbed photon, which is plotted on the right. So we can see above twice the band gap, the quantum will start to rise, and then it goes to about around 2.8 times the band gap. So this is quite good results in terms of the efficiency and threshold. Now we compared this with already known materials in literature. One was cesium lead iodide, but the band gap was too high, like 1.77 eV. And the other material was molybdenum ditelluride, which is a transition metal dichalcogenide material having a layered structure. And if we compare our tin lead halide perovskite with these materials, they compare really well in terms of the threshold and the efficiency. And it has, but the advantages are the band gap is favorable, like 1.2, 1.3 eV, and because these are bulk materials, the mobilities are quite high and it's easy to extract the carriers at the electrodes. So as I shown earlier that in case of symmetric transitions, where the energy is distributed equally between the electron and hole, the energy, the threshold becomes higher than twice the band gap. So when we observe a threshold close to twice the band gap, what can be the possible explanation? So as a possible explanation, it was proposed that there can be a second conduction band, or it's possible that there can be a second valence band. So there could be a second conduction band, and when that the energy of the second conduction band is like close to twice the band gap. So when we excite around close to twice the band gap, we create a hole in the valence band and the electron at the second conduction band. And now the excess energy is taken up purely by the electron. And then if we have favorable carrier multiplication, we get the threshold of carrier multiplication around twice the band gap. Now, this was verified in this in lead selenide or lead sulfide nanocrystals. So this is the band gap in this material. And here we can have two different kind of asymmetric transitions, like from the valence band to a second conduction band, or from a second valence band to the conduction band. And if we compare it with the experimental data, the threshold that is measured experimentally for the bulk and the quantum dots agree well with the energy of this L57 transition. That means the threshold close to twice, the threshold is like dependent on the energy of this asymmetric excitations. And if the asymmetric excitation is close to twice the band gap, we can have a threshold close to twice the band gap. Now this is the available band structure in this tin lead halide perovskite. So this is from a literature, slightly different structure. But as you can see here that there is a transition around 2.2 times the band gap in this material, where there is a possibility of a second conduction band, which agrees well with our experimental observation of the threshold close to twice the band gap. But this is like the DFT calculation where the band gap is like underestimated. So we need more advanced calculations to have a realistic band structure in this material to verify this model. Now, in terms of asymmetric transition, I just put one more slide. So this was a study by Quisser and co-workers. So the Socklet-Quisser, they calculated the maximum theoretical efficiency of about 30% in silicon solar cells, but they also did a lot of calculations how to go beyond this Socklet-Quisser limit. So this is one of the papers like in 1994 where they proposed that asymmetric transitions could indeed benefit the solar cells. So in this case, the material is an indirect bandgap semiconductor. It could be silicon or any indirect bandgap semiconductor. And they propose that if that material has a direct gap, transitions like twice or thrice the band gap and asymmetric energy distribution between the electron and hole, then that material could be good for carrier multiplication. So this was like a theoretical paper, and it's hard to get like a material that has this kind of band structure. And now in the tin lead halide perovskite, it's a different kind of asymmetric transition, but like the asymmetric transition really contribute to lowering down the threshold in different kind of semiconductor materials. So as a conclusion, for carrier multiplication, we need asymmetric transition where the excess photon energy is transferred either to the electron or the hole. The material should have small exciton binding energy to generate free carriers predominantly, and they should have high charge carrier mobilities for efficient charge carrier transport and collection at the electrodes. So tin head halide perovskites kind of fulfill all three criteria and could be good for multi-excitonic applications. So finally, I acknowledge my supervisor, Lawrence Sibylis, for supervising the project, our collaborators from AMOLF, Dr. Bruno Ehler's group for the samples, and NWO and Toyota Motors for funding. Thank you for your attention. So please let me know if you have any questions.